This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, let's kick this off. First of all, I'm just going to do an acknowledgement of country. Thank you so much, everybody, for gathering here. Before we begin today, I'd like to acknowledge the traditional owners, elders and knowledge holders of the unceded lands on which we gather today, the Wurundjeri, Woiwurrung and Bunurong peoples. I'd also like to acknowledge and pay my respects to those from all of the lands from which we all come tonight, including those of us joining online. It is our absolute privilege to work and learn every day with our Indigenous colleagues and partners, and we recognise the unique and enduring connections and custodianship Aboriginal and Torres Strait Islander peoples have with the lands and waterways across the Australian continent. Welcome to Physics Gymnasium 2024 Lecture 3. Shortly, we're actually over, we're halfway through this lecture, we'll be halfway. We have already been dazzled by astrophysics and spectroscopy and empowered by a discussion around geothermal power and our energy future. And Jacinta, if you learn one thing about me today, it is that I absolutely love dad jokes and puns, and I'm basically ready to be a dad. So still to come, we have that age-old question, light. Is it particle or wave? Or maybe both? And of course, a fun and fascinating foray into special relativity. But tonight we are here with Dr. Jacinta to learn all about how physics is changing the world of cancer medicine. Tonight's talk will go for 40 to 50 minutes, and we'll take questions at the end. I mean, if you see anybody going like this, feel free to take questions as you go, that's totally fine. I'll just ask you to repeat the question so that people online can hear it through the microphone. If you remember, if you don't, that's okay, all fine. We'll alternate between questions from the floor and questions online. So people online, if you're listening, there's a Q&A section. I have discovered how to turn that on this time, so please write your Q&A questions in there at any time. And if there's a sensible break and people are already asking questions, I will. Otherwise, we'll wait to the end and I'll very easily slide them in with our floor questions, just like people can't do when they zip merge. Over to Jacinta. Jacinta and I recently went for promotion from level A to level B, and we read each other's applications. She's actually amazing. The stuff I learned about her blew my mind, and I don't think I have permission to read it out, and I won't, okay? But her research combines the areas of accelerator physics, medical physics, particle therapy, developing technologies to improve the delivery of radiation for cancer treatment. She's got heaps of journal articles and conference proceedings, published in fancy research journals. She's got posters, grants and invited talks to her name already, and she's involved in a lot of really cool collaborations with people and groups around the world. She's also, I'm guessing still, an honorary research physicist with the Peter Mac Cancer Centre, which is really cool. She's also an important member of our School of Physics workforce. She's on lots of committees with me. She's my president, and is passionate about engagement with our communities, like you guys who are here tonight. So please welcome Jacinta Yap. I can't wait to hear about how physics is changing the world of of cancer medicine. Thank you so much. Let's go.
Thank you. Right. Alrighty. Thank you so much, Claire. Thanks for the kind introduction. It's really great to be here today. Thank you for all of you who turned up in person to hear me talk. Today I'll be giving an overview of the research that I've done within my fields of medical physics and accelerator physics. And really I'm going to talk about my journey to how I got here and basically how I progressed throughout my educational pathway to make it here to be a postdoc. So I'm going to try and fill in the gaps with physics, so hopefully everyone learns something by the end of this lecture. Okay, so just to start us off, I grew up in Perth, so I spent most of my childhood in the sunniest city in Australia. It's sunny for 320 days a year. It's also home to the world's happiest animal. So growing up, I was interested in sciences, problem solving. I really like to figure out, why something was wrong and how I could solve it. So my idea in terms of a career was something that you could really put your mind to and something where you could have a direct impact. I like the idea of using this knowledge towards human health, so naturally I lean towards a career maybe in medicine. It is very, very competitive to get into medicine, especially at undergraduate level though. So I ended up studying a degree in mechanical engineering and science, and my major was human biology and anatomy. So I went to UWA. I had 2 majors, which also meant that I would graduate with 2 degrees. It was a 5.5-year degree. Those 2 combined, though, in terms of a career pathway, the suggested career was a biomedical engineer. And to me, I wasn't completely convinced. So the University of Western Australia actually does what we do, the Melbourne model over here, which is where you do an undergraduate degree in, say, 3 years of science, and then you do a master's in a professional degree, do a master's in physics or something more specialised. So I switched to that, but still stayed in my engineering major, as well as I continued to do other subjects and things that I was interested in, such as chemistry, physics, biology. So when I thought back to high school and the stuff that I really like to do, think back to nuclear physics and, calculating radioactivity, looking at the decay chains, as well as really applying this to potentially treat cancers or diagnose cancers. That was something that I thought was really cool. I didn't know it existed in a career. So looking at my options, I really wanted to do something that combined engineering, so hands-on work, developing equipment, things like that, in combination where you could use this for human benefit, as well as solving real problems. So the combination of all of these, I feel like the overlap is pretty specific, but I came across this field of medical physics. So sort of towards the end of my bachelor's degree, I actually went on exchange. I came back and I figured the world is my oyster. I wanted to move, I wanted to travel. I wanted to do something else that wasn't engineering. So I applied for a bunch of postgrad courses around Australia. I got into a Masters of Science in Medical Radiation Physics at the University of Wollongong. So Wollongong's about an hour south of Sydney, and my degree was 2 years. I did coursework and a research thesis. I didn't know anyone in Wollongong, anyone in New South Wales, but I decided to just give it a go, see how things would turn out. So for those of you who don't know what medical physics is, it's defined as the branch of applied physics which employs physical concepts for the prevention, diagnosis, and treatment of human disease. So it's truly a diverse field that utilises the knowledge gained in other areas of physics and applies it to heal people. So the field is changing really rapidly. We have so much new technology that's being produced and being sold and being used. This translation to the clinic means that physicists are actually becoming increasingly essential in a wide range of clinical areas. So everything from radiotherapy, radiology, through to biomedical sensors and implants. So medical physics, in terms of your career pathways, it encompasses 4 main areas. Radiation oncology, which is really the treatment of cancers and other diseases, as well as nuclear medicine and radiology, so everything related to PET, X-ray, CT, so all to do with the diagnosis, as well as radiation safety. So there's many industries where you'll be involved with, say, delivering or using radioactive sources, and you need somebody who understands the physics of radiation in order to regulate and to handle these. So these all tie into 3 career professions as listed. So you've got your radiation oncology medical physicists, your diagnostic imaging physicists, and your radiopharmaceutical scientists. So in terms of these 3 professions, the requirements for those who are interested is typically a bachelor degree in something relevant, a postgraduate degree. So if you wanted to work in a hospital as a ROMP or a DIMP, you would actually have to undergo a 3-year training program. So you'd have to do the exams, etc. I also just want to mention that all of these areas, you can also do this as a research scientist. So you can work in a hospital and explore any of these areas. So you don't necessarily need to work as a clinical physicist to be able to have the same impact and to look at the same topics. So just to explain the workflow about how a patient gets treated. So if somebody thinks that they're unwell and they may potentially have something that could be close to cancer, they typically book an appointment with their doctor. They get referred to a radiation oncologist. So they would go to their clinic or their hospital, see their radiation oncologist, who would probably send them to go get scans done, so either X-rays or CTs. And then it's your radiation oncologist, who's your specialist medical doctor. They would actually look at these CTs and highlight specifically where the tumour may be. So it's your doctors who would diagnose and provide advice on the ideal course of treatment. These scans then get sent to your radiation therapists, who use something called treatment planning software to basically try and figure out the best way of getting radiation into these localized areas. Radiation therapists are also quite patient-facing, so when the patient actually undergoes their treatment, it's the therapists who they're with the patient, they're positioning the patient, they're making sure the patient is okay. And so typically the patient would lie on a treatment couch, that's what it's called, and you've got your linear accelerator, and this rotates around the patient and delivers radiation to the tumour site. So medical physicists are actually quite involved in this team. As a physicist, you need to be able to ensure that these linear accelerators and these machines are able to deliver the right amount of radiation, that they're accurate, and that patient safety is always of utmost importance. And it's not just the medical staff that are involved, but it's also your engineers, researchers, assistants, and lots of other people who really help patients get treated with cancer. So it's everyone on board. So now in terms of cancer, there are 4 main methods of treatment. So that's surgery, chemotherapy, of course radiation, and immunotherapy. So typically it's a combination of all of these. It's quite common that somebody will undergo treatment with radiation and chemotherapy. Ideally, the best way is to physically remove the tumour itself. So you might undergo surgery and you get the tumour completely taken out. Obviously, this is very invasive. But the trouble with this is that sometimes it's hard to tell how far the cancer has spread, or especially if it's spread to other areas of the body. Just removing it, the physical object, doesn't necessarily help. So that's why we have these non-invasive methods like chemo and radiation and immunotherapy. So what is cancer? Cancer is a large range of diseases. It's no single individual diseases. It manifests in many different ways, and basically it's cells which have an error and they keep multiplying uncontrollably and within different tumours, within different tissues and organs. It basically means that they aren't able to operate as per normal. So in Australia, almost 1 in 2 men and women will be diagnosed with cancer by the age of 85, and 30% of all deaths in Australia are caused by cancer. So obviously, as technology has improved, diagnostic methods have improved, the number of people being diagnosed with cancer is also increasing, population growth as well. But from the early 90s, you can see that these rates of people who have been diagnosed with cancer and have survived for more than 5 years, this is also improving. And that's because of all these different methods that we have and just how effective they are these days. So just to survey the most common cancers: prostate, breast, melanoma, GI, lung cancer, and the most deadly cancers: lung, GI, pancreatic, prostate, and breast. It's important to note that some of these cancers are just hard to treat. They may be radio-resistant, or if they're on say a mobile tissue, if you have a lung cancer, that's really hard to target and to treat because of the motion. So radiation therapy is used for to cure cancer, also for pain relief, and adjuvant, so to control the spread, and again, as I said, mostly combined with, say, chemotherapy, so these other methods of treatment. Typically, you would have X-rays which are used, or there's particles, electron beams, and protons and heavier ions. Typically, it's external radiation, but internal actually does exist, so something called brachytherapy, which is where you actually implant these radioactive seeds into the patient where the tumour site is. So this patient's currently in theatre, and you've got a doctor who's putting in rods which on the end have a radioactive seed. So if the dose rate is too high, no one can be in the room, so we have these robots which can do the same thing as well. Otherwise, the most common is external beam conventional X-ray radiotherapy, so using linear accelerators, which is this bit here. And so this structure here, that's called the gantry, and that can actually rotate around the patient, often 360 degrees. And this allows you to target the radiation at the tumour site from all angles. So there's different techniques to be able to do this, to be able to conform this radiation and how you deliver it in terms of the precision and the amount of dose. So these are some methods here. And typically a patient would go into treatment, so they'll have one session, which is about 30 minutes, although the machine might only be on for 5 or 10 minutes, but it takes time to position the patient. And so they'll go in for their treatment, and then they'll be done, and then they'll have to go in for the next day, and this happens Monday to Friday, typically for 5 to 6 weeks. It's really quite a long process, and it can be very taxing on patients, especially patients who have to travel. And so, yeah, cancer treatment is tricky, and we really want to make it better for everybody, for patients, for families, etc., for the whole community. So in terms of radiation, what actually is radiation? It's basically just a transfer of energy as waves or particles. So we have our electromagnetic spectrum here, which categorizes radiation as non-ionizing or ionizing. So if you have ionizing radiation, that's more harmful. It's got the highest energy, the highest frequency. So this is typically your X-rays, gamma rays. And ionizing means that it has enough energy in that it can ionize atoms, so it can knock out electrons, and this can change the chemical composition, the atomic structure of different things, which can have a detrimental effect. So in terms of our ionizing radiation, we have radiation with alpha particles, beta, and gamma rays. So there's something called linear energy transfer, which is basically the extent of radiation or energy transfer. So with alpha particles, they can be stopped by a piece of paper, which basically means that they can deposit all of their dose in a very, very short amount of space, which is a lot more harmful versus, say, gamma rays, for example, which don't stop, and they transfer a little bit of their energy as they go. So with linear energy transfer, this is a macroscopic description. So again, it's your energy, the amount of energy that's deposited in a certain material. When this translates to biological outcomes and biological damage, if we have, for example, a proton that knocks out an electron, this electron, so this atom becomes ionized, this electron can then bind onto hydroxyl molecules, which can actually break DNA pairs. So this is through indirect action, and direct action instead is where if you have, again, say a proton, for example, knock out an electron, this electron can actually interact with one side of the DNA helix directly. So these double strand breaks is basically an error in the DNA, which makes cells harder to replicate and to repair. And so the higher your LET via particle, so for example, photons have lower LET, because again, it's that long distance, so you've got this small amount of energy transfer, whereas if you have protons or heavier particles, they transfer all of this energy in a short amount of space that does more damage. So if you have protons that do more double strand breaks, it means that the cells themselves find it harder to repair. And so it's this kind of damage that we want to do to tumor cells. So the tricky thing, though, about radiation is that even if there's dose and energy deposited, radiation effects are stochastic, which means that they're probabilistic. So you can have two cells that have the same amount of dose or energy that's deposited, but you have the outcomes different. So one cell might continue to grow and repair, and another cell might die. And this is just purely probabilistic. So when you have staff work at hospitals or people who are exposed to radioactive sources, for example, we have these exposure limits, and that's basically to keep exposure down to a certain level because we don't want these probabilities of getting cancer later in life. So basically, the higher your exposure, the higher the dose, the higher the probability of side effects. Obviously, when you're treating cancer, you want to be above this threshold. So that's why they say, you know, to put on sunscreen, don't go to sun tanning beds, and to eat healthy, because it reduces the risk factors of getting cancer because it's probabilistic, and to reduce this probability of getting cancer later in life. So of course, if it's above a threshold level, then we get a deterministic effect. So we get that cell damage and death. For cancerous cells, this is what we want. So how can we measure this damage? So there are many physical ways of measuring this. So using detectors, we can measure the absorbed dose, the actual energy that's deposited in a volume or a mass. So if you have a bucket of water and you keep it under the sun, you can measure the temperature change, and this relates to the energy deposition. With equivalent dose, as I mentioned, there's alpha, beta, and gamma. So depending on the type of radiation, it transfers this energy in different mechanisms. So you need to apply a weighting factor, and then effective dose. So your organs and how they absorb this energy and how they're affected, there's different impact depending on the actual organ. So for example, if you get 1 gray of dose absorbed in your lung versus 1 gray in your skin, there's a very different outcome. So your detectors, they will give you physical quantities of energy, the number of particles, so flux, et cetera. But how do we actually measure biological impact? That becomes quite complex. So we have something called the relative biological effectiveness, which is RBE, and it's basically just a comparison between two different kinds of radiation. So typically the reference is to our conventional X-rays. And so, for example, if we compare the RBE of carbon, so if we want to decrease the survival of a cell to 10%, we require less dose compared to X-rays. And that's because carbon ions are 3 times stronger in terms of this radiobiological effectiveness. So to measure this is quite complicated because cells, there are processes inside which change how they respond to this dose deposition, how they repair, et cetera. But one way we can do this is through microdosimetry. So because radiation is stochastic, it means that it's hard. You need to compute all the different probabilities. But one way that we can do this is if we have lots of different events and we figure out what the mean outcome will be. So we can take the energy distribution between very small volumes. So imagine we have a really small volume filled with a gas. There's a single event that goes through which provides a charge. So we can see what this charge is over the mass. That gives us the energy transfer, which is similar to LET. And the microdosimetric term for that is linear energy. So basically, if you have lots of events, you get a distribution, you do some maths, and you can figure out a mean value. And that's what I did as part of my master's thesis. So at the University of Wollongong, they develop all these different novel detectors, typically made out of silicon. So you've got your semiconductor physics there. They had these detectors, which they were developing, and they did some first tests at a proton beam at a hospital in Boston in the US. And so this detector is actually tiny. You can see that this area here is 4 by 4 millimeters. And on this sensitive area, it's got 4,248 cells. So really, you can look at the charge for a single event. And so as part of my thesis, I had to compare these experimental results with Monte Carlo simulations. So Monte Carlo simulations are actually named after the site of this famous gambling location in Monaco, and it's a really common method of modeling things that are based on probability. So it's used in all different fields, especially physics, maths, as well as finance. And how it works is you define a start. So you have some boundary initial conditions and you generate, for example, we look at photons. So you generate a photon with a certain position of a certain energy, and then you have a probability of different events occurring. And then, so if an event occurs, then say the photon loses X amount of energy, then you keep progressing step by step up until an endpoint, say it loses all of its energy or it reaches a certain distance, and then you've got your outcome. So you can do this for lots of different events, and you can basically mimic what happens in real life to some extent. So of course, applied to particles and particle physics, you can do this by hand. Otherwise, there are bits of code and software that you can use to do this for you. So I used a software code called Geant4, which originated from CERN, originally for high energy physics, and it can model those interactions and the movement of these particles. It calculates all the probabilities for you. And basically, you just need to transport particles step by step. Of course, it's a bit complicated because you need to define everything about it, the geometry, materials, the parameters of your beam and the particles themselves. But using this, I was able to match our simulation data to experimental data. So after my master's, as you've just heard, medical physics, research projects, it's really a combination of everything, isn't it? It's a bit of programming, some maths, lots of physics, detector stuff, radiobiology. Looking at the big picture, however, this is all really to progress and to improve the effectiveness of treatment, in particular, proton therapy treatment. So if you use protons instead of X-rays, you can actually have a much more precise and targeted dose rather than X-rays, and specifically to where the tumor site is. But the issue is that with this is that you require much more expensive machines. So your accelerators are much, much bigger, way more expensive, and you need large facilities and lots of shielding for this. We don't actually have any in Australia. And so I was really keen on particle therapy and learning more because I thought that there's great potential and this is the future for radiotherapy. So towards the end of my master's, I was sort of tossing up between medical physics, clinical training, or doing a PhD. I come from a family of engineers and accountants, so nobody worked in academia, nobody had any idea what it would be like. But nevertheless, I applied for PhD positions and I got one at the University of Liverpool, the Cockcroft Institute, and the title of my project was Halo Dose Correlation in a Medical Accelerator. So it sort of sounds like what I was doing for my master's project, which is developing a novel detector for proton therapy again. But yeah, it sounded cool. So this is me. I graduated in July and then moved to the UK in September. Now for my PhD, I did this in the northwest of England in Liverpool, which is just here. And we have some famous products from Liverpool here. So my PhD was a 3-year fellowship, and you do it for 4 years. I was employed as a Marie Curie Fellow, part of the European training program called the Optimization of Medical Accelerators, or OMA. And there was basically 15 of us spread across Europe, based at research institutes and major particle therapy clinics. We had a really extensive program. There were schools, workshops, conferences, etc. And the idea for OMA was really to progress particle therapy and to contribute to the field, particularly in these 3 areas. So developing beam imaging and diagnostics or instrumentation, optimizing that treatment planning process, as well as facility design, some more of the accelerator stuff. yeah, so the overall goal was really to try and improve and assure the best possible cancer care for patients. So what this looked like, there was 15 of us all across continental Europe and the UK. What this really meant was lots of site visits, conferences, presenting at conferences, me at CERN, more site visits, presenting posters, doing actual work, so experimental testing, presenting at more conferences. But really, like doing a PhD, the best thing about it is the social stuff. It's the people that you meet along your journey, and drinking and visiting foreign locations. And yeah, just all the people that you meet along the way and the stuff that you do even after that's finished. Yeah, so onto the work. My PhD project was more in accelerator physics. So the field of accelerator physics is really about designing and studying accelerator technology. So developing the instrumentation, characterizing and modeling facilities. And the thing about accelerators is that you can model it, you can, write all the equations, do all the theory that you want, but when you actually build it, it becomes very different. So you need to consider different operational and practical aspects. So accelerator physics is very multidisciplinary. You wear a lot of hats. There's a lot of engineering, optics, you're a computer scientist, magnet and detector stuff involved. So for my PhD specifically, the idea was to translate experimental equipment to be used for a clinical environment, so specifically a proton therapy clinic. And of course, your work contributes to the larger body of work. And for me, that was particle therapy. So when you're delivering a treatment, it's really, really important in terms of the technology, so the accelerator, that you're able to measure important information about the beam before you turn it on, after you turn it on, and during treatment. And again, this is to maintain patient safety and that you get a high quality of treatment. So some important parameters, the amount of dose you're delivering, the beam intensity or the current of your beam, the shape of the beam and the position of the beam. There is no one device that does all of this. You have many devices, but not all of them are built in the same way or they work as well. So with all the new delivery techniques and technologies we have, we need to develop detectors to catch up with this. And the detectors that we have now, we need to improve. We need faster, more accurate methods, as well as methods to be able to measure the beam without interrupting it. So my PhD project looked at the development of a novel online dose monitor. So if you imagine this is a proton beam, you've got your beam and it goes through air, interacts with particles in the air, which creates a halo, which surrounds the core of the beam. And you can actually measure this. So using this novel detector, which basically is like a CD split down the middle and it's got a hole through the center, you can measure around the beam, can model this. And if you correlate it to experimental results, then you have an idea about the beam current in real time. That was the idea for this detector. So this detector was actually based on CERN technology, so at the Large Hadron Collider. The LHC is the world's biggest lab, the world's most expensive lab. It's probably, the LHC is probably the most precise bit of equipment that's ever been made by man. It's just phenomenal how everything works and that it was able to be run. So the detector that I had was originally used for the beauty experiment, LHCb, which is here. Another note about the LHC is that it's 27 kilometers long in circumference, so it's absolutely massive. It's underneath the countries of France and Switzerland. You sort of have to bring your passport everywhere when you're there because you're constantly crossing borders. So you could be working in France and have lunch in Switzerland, which is a really strange concept. I had colleagues who on their lunch breaks went to ski because it's so close to the mountains. It's really a different world over there. But yeah, so my PhD project based on these detectors at LHCb. So it looked like this. My university was actually involved in the development of these. So we had just a spare set in the lab and the idea was thought to see if we could translate this technology. So from a high energy physics, high radiation hard environment into something that could be used for the clinic. So in a nutshell, in order to integrate something into a facility, you need to understand the facility really well. So with a treatment facility, you often don't have as much equipment or instrumentation as an experimental lab. So sometimes it's a bit difficult to find out this information. One thing that I did though, I was able to model at least the treatment room. So physically measure and then build this in CAD, and then I could import that into this Monte Carlo simulation code as well. How do we model a facility? So besides the treatment room, it's really important to be able to understand what's happening upstream. So in the bunker where the accelerator is, and how your magnets focus and steer the beam, and what the behavior of the beam looks like as it comes out into the treatment room. So one way of doing this is to find out what the specs of your magnets are, what the different fields are, to measure the distances between, and to try and model this. So you can sort of do this to a certain extent, but then you need to do experimental measurements to match it. So I did a whole bunch of measurements at this clinical facility, including film measurements. So this gives you an idea of the shape of the beam. And then we did some benchmarking with another detector. And this is actually what the beam current looks like in real time, which is pretty cool. And then for the main part of my thesis, what about Velo? Because these detectors were actually what my PhD was supposed to be about. So as often happens in a PhD, things always go wrong. And so the idea was to develop these detectors to be implemented into a clinic, but there was just no way we were going to get all of this kit into a treatment room, given the time constraints and resources, et cetera. So our contingency plan was to instead bring all of this equipment to an experimental facility that also had a proton beam, just so we could test our system upgrades and further develop these detectors. So again, looking at all of these developments to contribute your little piece of knowledge to this body of work, which is particle therapy. So as I mentioned, it's the most advanced kind of radiation therapy because it's super precise and really accurate. So with any therapeutic drug, we have something called the therapeutic ratio, which is basically two curves. So if you have a drug, you want it to have a certain good effect before there's a side effect. So this difference between the two curves, that's your window. You want to stretch that out so that you can do lots of good before there's harmful effects. So the idea with particle therapy, with proton therapy, is you're able to have higher effectiveness. You're able to deliver this radiation dose with less of the harmful effects. And that's due to the dosimetric characteristics of charged particles. So I've been saying particle therapy and proton therapy interchangeably, but protons are particles. So they're a type of particle therapy. They're the most common though, and they're the most common because they're the lightest. The heavier you go, the bigger machinery you need, the bigger accelerators, the stronger magnets, et cetera. So protons are the most common. Protons have a higher LET, so they do more radiobiological damage. And again, this means that you have this higher probability of double strand breaks and DNA damage. So photons deposit and transfer their energy pretty differently to charged particles. So we have something here called the depth dose curve, which is basically the distribution of energy transfer in a medium over a certain depth. So with photons, the further away you get from a radioactive source, you get this drop off of energy. And then attenuation, basically the probability of transferring more energy increases if you have a more dense material in general. That's because there's high probability to hit more particles to transfer this energy. And then you have a buildup because usually photons, they come into contact with an electron, for example, and it scatters it far away. So they deposit their energy elsewhere. And so all combined, this gives you a depth dose curve that looks like this. So you have most of your energy transfer right at the surface, which if you think about it, isn't super ideal for deep-seated tumors. Protons, on the other hand, we can look at this energy transfer through stopping power. So energy loss over a certain length. And then if we take into account density for different materials, so protons lose their energy through 3 different kinds of interactions: electronic, radiative, and nuclear. So there is a complicated equation which models this. So there's factors in there for relativity, et cetera. But basically it looks like this. And you can see that it's also not linear. So protons, as they traverse through matter, they will actually come into contact with electrons and ionize them, or they'll bounce off them. And this means that your initial proton will slowly lose energy, or either stop or it'll slow down. There are also nuclear interactions which may happen, so your proton might get absorbed and produce other secondaries. But in general, so as they slow down, the probability of interactions increases, and you've got this energy loss over shorter and shorter distances. And this basically accumulates something called the Bragg peak. So you can see with protons, they lose basically a maximum amount of their energy at a certain fixed point. This is called the Bragg peak. And where this Bragg peak is within matter, within a medium, this is determined on the initial energy of your proton. So this basically means that protons go a fixed range within tissue, within water, within the human body. So again, if we look at X-ray photons, so it's a very different distribution. So what happens if we have a tumor that, again, is quite deep-seated? How do we irradiate only the tumor while preserving healthy tissue? This becomes difficult to do. So instead, we can actually use protons, which have this Bragg peak, which, based on the energy, we can target specifically the tumor. But again, tumors aren't necessarily 1 centimeter thick. So what happens if we have a larger tumor? Well, we can actually superposition lots of Bragg peaks. So this is called the spread out Bragg peak, which gives you you get a resulting dose distribution that looks like this green curve. So that's based on lots of Bragg peaks of protons at different energies. And so if we have a tumor that's this wide, for example, you can just change the beam energy and conform the amount of radiation specifically to the shape and position of the tumor. So what this looks like in reality, so again, it's this Bragg peak, and having that no dose afterwards, which is really, really beneficial, because that means that if you have organs at risk, critical organs right behind the tumor, you don't do any damage to them. Whereas with X-ray photons, the beam goes straight through. So what this looks like in treatment. So we have 2 treatment plans here. Ideally, we want to irradiate this area in the red. There's a tumor in there somewhere. So with X-ray photons, you see there's radiation all over. They go straight through the patient all around. But with protons, we're able to adjust the beam angles so that it stops and doesn't go into this side of the body. So this is the real benefit to protons. And the heavier you go in terms of ions, the higher the LET and the higher this biological effect. So you may be wondering then, why don't we treat everybody with particles? Why don't we use proton therapy everywhere? So with cancer treatment, only around 40% of treatments use X-rays, and less than 1% receive proton therapy. So all around the world, there's only about 130 facilities, which isn't a lot. And you can see it's mostly concentrated in continental Europe, the US, and a few in Japan. It's mostly developed countries. So there's a few challenges why it's not widespread. So in terms of the biology, the physics, and technology, we know that it's superior in terms of the physical sense. It's superior to X-rays, and we haven't reached the full potential. But the problems that still need to be addressed is the costs and limitations with our technology. So within X-ray LINAC, it's a few million US dollars, depending on what model you buy. How it works, you have a power source, which is connected to your electron gun. So basically heat up piece of metal, cathode, really hot, and then it emits electrons. There's a potential difference. This goes across from cathode to anode, and they get injected into the accelerating waveguide. So this waveguide is made up of multiple cavities, which get fed an oscillating electric field from this pulse generator. And electrons, as they enter this waveguide, they sort of ride this wave and they get a kick of from this RF and electric field as they pass through at just the right time, and this accelerates them along the waveguide. So you can do the same thing with standing waves. So it's at the right time, bunches of electrons get this kick, and this is how they're accelerated down. So electrons then get deflected by a magnet toward the patient, and they hit a target that's usually made out of tungsten or something that's got a high stopping power. And this slows down electrons, and they release energy through Bremsstrahlung, and this produces the X-rays. So these X-rays are then shaped by various bits of typically metal, and you can actually collimate them down. And there's something called multi-leaf collimators, which are basically bits of metal which shape the beam to the shape of the tumor. So this is a video, hope it plays, yeah, of how it looks. So you can see that gantry rotates around the patient, and this is the beam of X-rays. And you can see that the leaves actually move as the gantry rotates around the patient, and this is how you deliver this targeted conformal amount of radiation. So they move in and out. You have thinner leaves and thicker leaves. It's painless. As a patient, you're just supposed to sit there as still as you can for 30 minutes, which is actually quite a long time. But yeah, so you can see in this video that the beam goes straight through, and that's because you're using X-ray photons. Cool. Okay, cool, yeah. So as I mentioned, these X-ray linacs are a few million in, say, US dollars, for example. For a proton therapy facility, it's 10 times the price. And so if you have something that costs 30 to 50 million for just a single treatment room, then it becomes exorbitant. The hospitals can't really afford this. And not just that, but that gantry bit on the end of the linac, which rotates, you now have to have an entire assembly because you're using charged particles. And so this is sort of separate to the accelerator. With carbon ions and heavier, you need to go much, much bigger. You can see that this is the accelerator and this is a person, and the gantry itself is absolutely massive. And that needs to turn to adjust this charged particle beam within, sub-millimeter precision. So it's pretty complex. And like really it's the cost. It's basically mostly first world countries, developed countries which can afford this. So that's a huge inequitable problem that we also need to fix. But yeah, so just like with X-ray radiation therapy, you have an accelerator as your source, and then it goes through some sort of beam transport and goes around to a gantry, which rotates around the patient. With particle therapy, it's a bit different because you have this third dimension of depth. So how you actually direct the beam of radiation to the patient is there are magnets, and basically you paint across layer by layer. So you paint across in one layer, and then you adjust the beam energy, so you lower it, and then you paint in the next layer. And there might be 30 layers just so that you can get enough coverage of this 3D volume. So in a treatment, the total time is made up of how long it takes to set up your patient, the actual beam delivery, and then how long it takes to do these checks. So we can improve the accessibility to particle therapy if we can reduce the costs, make delivery better, and if we basically just have smaller, better, and cheaper machines. So as I mentioned, you need to shift between the layers, and this is really a technological limitation. And this is due to the capabilities of your beam delivery system, which is those magnets here. So from your beam transport and around your gantry. So these steer and focus the beam to the patient. But because with particle therapy, you constantly need to change the energies, that means you need to wait for all of the magnets to reset to change their fields in order to deliver the next energy. So because of this introduces a bottleneck delay. And we don't want to treat slow because the patient is moving, organs are moving. if you want to irradiate at a certain spot across a few seconds, this may change because of just how the patient is breathing and how these organs move within the body. So really, how fast we can treat also impacts how well we can treat patients. So one way of improving this, we need a technological solution, and that's to increase something called the acceptance range. So basically, if you design your beam delivery system such that you can deliver lots of different energies without needing to change the magnets, then you can potentially get rid of this dead time. So if we look at this animation here, if you have bunches of beams of different energies, they can all travel through the same beam pipe and same magnets all at the same time. This is pretty different to normal, because normally you would want all of the energies to be delivered and to be transported straight through the middle. But this is something we can do if we completely redevelop the beam delivery system. And we do this through using a novel concept of accelerator optics, building our own custom magnets. There are lots of physics challenges. Nobody in the world has solved it. For one, it's obviously really expensive and difficult to build this full scale. And firstly, we need to prove that this concept will actually work. So you need to build something small scale and then scale it up eventually for clinical implementation. So that's what's led to my current project, which is Turbo, Technology for Ultra Rapid Beam Operation. So that's what I'm working on now. So we're building a prototype, low energy, because we do have a proton accelerator here. It's actually in the basement just next door. We are building an entire brand new beamline assembly because it's this prototype of that beam delivery system. So it means that we need to model everything, design everything from scratch, basically. One of the cool things that we're doing is, so we had a PhD student who worked on this, and basically you can arrange the magnets in a way, in a clever way, so that they end up generating the magnetic field as you need. So you can 3D print the holders to store bar magnets, which you can just buy online. So because we have a smaller scale, a low energy accelerator, we can actually do this and build our own magnets from scratch. So of course, this project is pretty extensive. We're only just getting started. Hopefully we can start building very soon. But of course, there's lots of work involved. And hopefully at the end of this, we'll be able to build something that can potentially push forward with these limitations and contribute to the improvement of particle therapy. So just some closing messages. I work at the overlap of medical physics and accelerator physics, which are both really exciting areas to work in. There's just so much happening all the time. There's many different aspects and areas of physics where you can apply the stuff that you've learnt. It's not just equations and theory, but really we have societal and health benefits. So the field needs lots of bright, diverse and determined minds. So again, don't be afraid to dream, move across the world and to study more and pursue your ambitions. Thank you for listening.
Jacinta, what an amazing talk. I actually know barely anything about this. I mean, I know everything.
It's a very
right?
niche field, yeah.
But I've never sort of sat and thought about this, and it's mind-blowing, actually. I think it's quite incredible how physicists sort of got their hands in everything. Right?
Everything, literally.
We talked about power a couple of weeks ago, and we're talking about spectroscopy and astrophysics, that's normal. But I mean, the sort of, cancer is going to affect 1 in 2 of us if we live till 85, if we're lucky enough to live to that age. And then most of us will know somebody that is affected. And to know that people like you are putting your mind to this, I think is absolutely incredible. And I think we're extremely lucky, actually, to have this sort of science going on, especially at the University of Melbourne. I used to know a very good joke, but it's now only half as funny. I'm really sorry. Sorry about that as well. What do you call an optimistic person with radiation poisoning?
No idea.
Toxic positivity.
Oh.
Okay. You don't know
that wasn't too difficult, yeah.
Most of the people that come here regularly will know that there's always 1 or 2 really bad jokes that happen at the end, and it makes everybody feel good about laughing, mostly at me. But it's time to ask questions. So if anybody's got a question for Jacinta, please put your hand up. I mean, I've got a couple, but I'll let you guys kick us off. Yeah, over here.
When you're using proton beams, what's your source of protons? Are you just knocking electrons off hydrogen atoms, or how do you actually get the protons?
Yeah, so usually it's just hydrogen gas, and then you ionize that and inject that into your accelerator.
When you're figuring out like the depth dose ratio, like how deep to go into someone, what diagnostic would you have to do on a person to figure out like the density going through?
Yeah, so this is actually an ongoing problem because obviously the body is not one density. So we can't actually do this in vivo at the moment. It's all based on your calculations beforehand. So you can do X-rays. So it's easier with Linux because you do an X-ray with a photon and then you treat with a photon. But with protons, it's a lot more tricky because it's this stopping power conversion when you try and correlate an X-ray with photons versus protons and the density and how far it goes. That's a lot harder to correlate. Yeah.
I think, did you have a question? I think that's
Me?
yeah.
Oh no, I'm
No?
just going, whoa.
So mine's on.
Physics.
Amazing.
Yeah, maybe it's fine. So, yeah.
We'll go here first, so we'll kind of go, we'll go to you.
I'm wondering if are there any other particles that are showing particular promise in this area that just haven't been used in the past that perhaps could be run at a lower cost than proton?
Not really. So before protons, there was neutrons, but they're way harder to use. Helium and everything charged basically has that same Bragg peak. Protons are the lightest though, which makes them the cheapest and the easiest. Exactly. Yeah.
Heavier particles require so much structure and size of
Yeah, because you need higher magnetic fields to bend them, yeah, and to accelerate them, yeah, which means that your machines just get bigger and bigger.
Any questions from online? So if there's anyone else, hello?
Thanks for the talk. It's just fantastic. I'm fascinated about how many different skills you have to apply to this. You do just everything, don't you?
A little bit, yes, yeah.
Machinery that you have designed, that you actually get your hands dirty and build things yourself. Like if you got a soldering iron out,
Yeah.
a screwdriver and a hammer and something.
Yep, so surprisingly, we do have all those tools like in the lab. And so we used to have a workshop here in physics so that we could do it in-house. We haven't started building, but at some stage we will need to do everything by hand to, screw things in ourselves, that sort of thing.
Is that as much fun as the maths that you do and the theoretical physics?
I think for me, so coming from a background in engineering, like for sure, I'd rather do the hands-on stuff than, sit at my computer, fix a bug in a code.
With the current project, trying to get more than one beam in the machinery,
Yep.
does that mean you have to run like 5 different beams through the particle accelerator too? Like, does it go all the way back to the start? Like, you need to generate more protons and accelerate more.
Yep. Yeah, so basically we're just replacing that end part, that beam delivery system. So that's the part that we're making more efficient. So all the protons get generated as the same that comes out of the accelerator. Yeah, that answers your question.
I've got a tag on to that one actually.
Yes.
So if you've got different energies of protons all coming out at the same time, I'm assuming that you don't have any interactions between them. Is that another difficulty of this?
Yeah, no, although, so we have been asked this question like about simultaneous delivery. So do we just want to blast protons at all different energies through? The answer to that is no, because that makes it a lot more harder to ensure and verify that you're hitting the right spot. Anything to do with medical, if it's a bit unsafe, it's completely gets thrown out. Yeah, so ideally we want to do discrete beams of discrete energies and multiple beams just quickly. Yeah.
I see. So you're speeding it up at that one energy so that you can then move to the next one.
Yep.
Is that correct?
Yeah, exactly.
Cool. Any other questions?
Is there potential for multiple delivery pathways so that we can have
different energies, photons coming through different streams, but then coming out at the same point?
With photons, not with protons, yeah. Sort of. So there are combined therapies, so using different particle sources. So, for example, if you use helium or carbon, that Bragg peak becomes a lot more steep. So if you have a beam delivery system that can accept wide ranges of energies, if you have a different particle type, it may also be able to accept it if it's within the boundaries. So in this case, then yeah, you would be able to treat using the beneficial characteristics of your different particle types.
You have another question?
Yes.
Always comes up with the difference between the pros and cons of having the radiation therapy any kind. So I don't know if it's used for you, but generally a machine like this that will be going to cost too much. Would there be studies that will tell us that how much like a single patient would have a benefit versus the side effects of therapy? It's because it's like compared to the other one has like double or 3 times the price.
Yep.
So
you're talking about the cost effectiveness and studies into that? Yep. Yeah.
The data for the
Yep. So protons are still more expensive. It's complicated. There's been many studies that have been published. It's complicated because different regions in the world have different healthcare. So in the US, that's really hard to compare to places in Europe, for example, because there's no private healthcare there. Sorry, no public healthcare there. It's only private. So the costs sort of fluctuate. There's something that's called quality adjusted life years, where basically if you treat with a treatment that's less effective, the risk of getting cancer later in life is higher, and that can potentially end up being more expensive. So there are arguments in this case. In any case, protons become more expensive, but the current trends in the technology are looking at having cheaper, smaller systems, so single room, 1 accelerator, 1 patient, rather than these massive facilities that have multiple rooms because they just are way too expensive.
When you're like sending like the proton beam to the tissue,
yep.
When it's traveling through healthy tissue before, which is the Bragg peak, is the energy that's releasing on the way, is that enough energy to ever like cause a double strand break? Is that ever like pose a risk of leaving that radiation energy tissue as well? Yeah, potentially. So I think. Yeah, so it's a tricky thing because you sort of compare to current methods, which are X-rays, and with X-rays, for sure, you're going to deposit more energy anyways. With radiation therapy, the aim is to deliver as much or sufficient dose to the tumor while doing as little as you can. But as long as you deliver that sufficient dose to do the intended outcome, which is to kill that cancer, then that's all that matters. I'll just go back to the Bragg peak so you can see there is a surface dose. Yep, so here, but you can see that with X-rays that far outweighs. Yep.
I think I might call it there. I'd like to thank Jacinta again. Thank you so much. I've got a book for you. There we go.
Thank you.
The very funny thing about this is that this book here is written by Jacinta's supervisor. No doubt she already has a book, so it was kindly donated by Susie Shue. I'm sure it's a great read.
It's a good book.
Yeah, it's a good book.
Yeah.
So thank you so much. I'm just going to quickly share my screen if that's okay. Just to let you know, we have got 2 more awesome where's front share? Oh, look at me go. Okay, we've got 2 more coming up, and I need to put it onto the lectern computer. Let me go. Very exciting. So we've got 2 more coming up. We've got Professor Harry Quine, who's our head of school, who will be talking about wave or particle, the enigma of light. Now, I've already been told off for using the word enigma because he doesn't like it. So make sure you mention it a lot in your questions to Harry. Make sure you say it's such an enigma every time you ask a question in 2 weeks, please. That'll be very funny. And have nothing to do with me setting it up whatsoever. So that's here in 2 weeks. If you haven't had your QR code scanned today, please come down and make sure I scan it before you leave, because it just helps us with funding, so we can say we've had this many people. And of course, we've got our final one there, which you can only see half of. That will be on special relativity. That's in 4 weeks. So we've got 2 weeks, and then 2 weeks after that, we've got special rel. We really appreciate you coming along, especially the people I have seen over and over and over again. I hope you enjoyed that talk as much as I did. And we've got 2 more to go. And just a really big thank you to Jacinta once more, and thank you very much.